students, I hope you understand the concept of p-value and the concept of confidence interval. And with these functions, it becomes very easy for us to calculate all this, because here we are not looking into the tables and we are checking the values and the degrees of columns and the critical value. Everything is done with the help of the R function. We are just passing the values, which are the parameters, like the sample A, sample B, then mean, then standard deviation of the first series, standard deviation of the second series. Rest of the computation is done by the function z.test. ANOVA. So let's talk about ANOVA now. ANOVA is very popular test and it is also used in R programming. ANOVA, also known as analysis of variance, is used to investigate relations between categorical variables and continuous variables in R programming. So mainly, ANOVA is analysis of variance, that what is the variance, and it is used to investigate the relationship between categorical variables, that are they related or not. So it is a type of hypothesis testing for population variance. So basically, again, for the ANOVA, it is a hypothesis testing, because when there are two variables, we try to find out whether they are related to each other or not. So our ANOVA test is very common test, and this involves a little function of R. Let's talk about ANOVA test, which involves setting up. First of all, we need to have a null hypothesis. We know that all population means are equal. Alternative hypothesis, at least one population mean is different from other. So what null hypothesis says, that the population means are all equal, but alternative hypothesis says that one population mean is different from another. ANOVA tests are of two types. So there are two types of ANOVA test, one-way ANOVA and two-way ANOVA. So one-way ANOVA, it takes one categorical group into consideration, and two-way ANOVA, it takes two categorical group into consideration. Now, let's talk about our data set and see what is happening. The data set empty cars, which stands for motor trend car road test data set, is used, which consists of 32 car brands and 11 attributes. The data set comes pre-installed in DPLYR package in R. To get started with ANOVA, we need to install and load the DPLYR package. Performing one-way ANOVA test in R is very simple. One-way ANOVA test is performed using empty cars dataset, which comes pre-installed with DPYLR package between disp attribute, a continuous attribute, and gear attribute, a categorical attribute. So you can see disp attribute is a continuous, where the values are continuous, and gear attribute is categorical, where the value is into some categories. Let's have a look of this code and understand what's happening. Though this looks quite complex, but it is not. It is very simple. You can see over here, we have installed the package DPLYR. So installing the package, after that we are loading the package with the help of library functions. So top 4 lines are just about installing the package and loading the package. After that, we are calculating variance in mean within groups and between groups. So what is the variance in mean within the group? That within the group, what is the variance? And then between the group, between two groups, what is the variance? So we are doing that with the help of box plot function. So you can see over here that the box plot function has empty cars data frame, where we are pulling the disp attribute. And then we have factor, where we are doing the factor of empty cars, and $gear means we are doing factors of gear. X label is gear and Y label is disp. So now you can see that the step 1 is set null hypothesis and alternative hypothesis. Your null hypothesis says that mu is equal to mu1 is equal to mu2, which means there is no difference between average displacement for different gears. So this is our null hypothesis, which says there is no difference. Keep one thing in mind, students, that null hypothesis always say there is no difference. It is equal. It talks about equality. But when it is alternative hypothesis, it talks about unequal, less than, greater than. So that is the basic difference between null hypothesis and alternative hypothesis. So here, null hypothesis say that mu1 is equal to mu2 is equal to mu. So here we can see H1 is alternative hypothesis, which says not all means are equal, which means mu1 is not equal to mu2 or mu2 is not equal to mu3, means all the means are not equal. In simple words, if we say these two hypotheses are saying that null hypothesis saying that all means are equal, An alternative hypothesis thinks that all means are not equal. Now, after setting the null hypothesis and alternative hypothesis, we come to step 2, which says calculate a test statistics using AOV function. Empty cards underscore AOV is equal to AOV and within brackets empty cards dollar display factor empty cards dollar gear. So here we are calling the AOV function and then summary empty cards underscore AOV. Step 3 is calculate F critical value. So after calculating the summary, we are calculating the critical value, which is the value that decides whether we have to go with the null hypothesis or we have to go with the alternative hypothesis. So for 0.05 significance value, critical value is equal to alpha is equal to 0.05. Step 4, compare the test statistics with the F critical value. So basically our test statistics is one thing which comes and critical value is the F critical value, and conclude test P is less than alpha, reject the null hypothesis, which means our critical value is less than alpha. In that case, we reject the null hypothesis. So that is how ANOVA is applied. You can see in the graph that these are the box plots which are going, and these are 5-number summary. You can see that in all the 3 plots, the third gear is the mean is quite high, the median is quite high, whereas in the 4th gear, the median is quite low. So that is how we understand the box plots. Now, let's talk about two-way ANOVA test in R. So two-way ANOVA test in R is performed using empty cars dataset, which comes pre-installed with DPLYR package between disp attribute, a continuous attribute, and gear attribute, a categorical attribute. So again, we have installed the package DPLYR and we are loading the package library DPLYR. Now, variance in mean within group and between group, box plot, empty cars $disp, empty cars $gear, subset is equal to empty cars $am equal to 0. And there xlab is equal to gear, ylab is equal to disp, main is equal to automatic. And likewise, box plot, empty car $disp, empty car $gear, subset is equal to empty car $am equal to 1. Xlab is gear, ylab is disp, and main is manual. So that is how we are creating the box plot. Let's see what we are doing here. Our first step is set the null hypothesis and alternative hypothesis. And again, H0, our null hypothesis says that mu1 is equal to mu0 is equal to mu3, which means there is no difference between the means of all average displacement for different gears. So for all the gears, the mean is same. Whereas H1 says not all means are equal. Our step 2 is calculate the test statistics using AOV function. And here we have calculated the test statistics. AOV, within brackets, we pass empty cars column display and factor empty cars column gear multiplied by factor empty cars AM. And that value is stored in empty cars underscore AOV2. Now summary, empty cars underscore AOV. And step 3 says calculate F critical value for 0.05 significant value. Critical value is equal to alpha is equal to 0.05. And step 4, compare test statistics with F critical value and conclude test P less than alpha, reject the null hypothesis. So basically, if P is less than alpha, we have to reject the null hypothesis. And you can see the 2 plots over here. Let's talk about chi-square goodness of fit test in R. A shop owner claims that an equal number of customers come into his shop each weekday. To test this hypothesis, our researcher records the number of customers that come into the shop in a given week and finds the following. Monday, 50 customers came. Tuesday, 60 customers came. Wednesday, 40 customers. Thursday, 47 customers entered. And Friday, 53 customers. So basically, the shop owner was trying to claim that equal number of customers come into his shop every day. So the statement was that all the days, all the customers are of equal number. But when we are testing the hypothesis, we recorded the number of customers for every day and we found this data. So data says something different because every day the footfall is different. So use the following steps to perform a chi-square goodness of fit test in R to determine if the data is consistent with the shop owner's claim. So basically, the idea is that with the help of chi-square goodness of fit test, we are trying to figure out that what the shop owner is trying to claim is as per what data has been collected. So sometimes it happens that the fitting of the curve is exact, which means what the owner has claimed, the shop owner has claimed, is exactly same what data has been collected. But sometimes it differs. So if it differs, how much it differs, that matters. So now let's see that what we will do in the chi-square goodness of fit test. First, create the data. First, we will create two arrays to hold our observed frequencies and our expected proportion of customers for each day. So observed is 50, 60, 40, 47 and 43. Now why we are calling it observed? Because this is the data that we have recorded. And what is expected? Expected is that it is same. It is same for all the days, which means it must add up to 1. 1 means 100%. So now the expected value becomes 0.2, 0.2, 0.2, 0.2, 0.2, which comes to 1, 0.2 plus 0.2 plus 0.2. So observed is something else that we have collected, and expected is something that the shop owner is claiming that it is equal for all the days. So it must add up to 1. So now we perform the chi-square goodness of fit test. Next, we can perform the chi-square goodness of fit test using the chi-sq.test function, which uses the following syntax. Chi-sq.test within brackets x and p. X is a numerical vector or observed frequencies and p is a numerical vector of expected proportions. The following code shows how to use this function in our example. Perform the chi-square goodness of fit test with the line chi-square.test, which is our function name, x, which is our observed data, and p, which is our expected data. So chi-square test for given probabilities are data observed, x square is 4.36, degree of freedom is 4, p value is 0.35. So you can see over here that when we pass the value, we get such kind of result. X squared is 4.36, degree of freedom is 4, and p value is again 0.35. Now the point is that how to interpret this data. So the chi-square test statistics found to be 4.36 and the corresponding p value is 0.3595. So students, now how to understand that what this tries to say. Note that the p value corresponds to a chi-square value with n-1 degrees of freedom, where n is the number of different categories. In this case, it is 4 because 5 minus 1. Why 4? Because 5 cases were there, 5 days were there, n was 5 and therefore degree of freedom is 1. We can use the chi-square to p value calculator to confirm that p value that corresponds to chi-square is 4.36 and degree of freedom is 4 and the value is 0.35947. So students, this is the value of p that we have got. Let's understand and interpret it now. The chi-square goodness of fit test uses the following null and alternative hypothesis. The null hypothesis says a variable follows a hypothesized distribution. And alternative hypothesis say a variable does not follow a hypothesized distribution. So null hypothesis was it is a hypothesized distribution that it is same. But alternative hypothesis says that it is different on all the days. So since p value, which is 0.35, is not less than 0.05, we fail to reject the null hypothesis, which means we accept the null hypothesis and we reject the alternative hypothesis. This means we do not have sufficient evidence to say that true distribution of customers is different from the distribution that the shop owner claimed. So basically, we can say that we do not have sufficient evidence to say that the true distribution of customers is different from the distribution that the shop owner claimed.